So most of you will find what I'm going to talk pretty elementary, and that was the idea. So the idea was to sort of cover some simple ideas in probability theory, so that when people start talking about probability distributions and statistics, we are not left behind, and everybody is on par with the notation and the ideas. So how many people have seen probability theory before? Just give me a hand. So most people have seen. And who has never heard of probability theory, probability distributions? Most people have seen and heard. People have heard of moment generating functions? Who has not heard of moment generating functions? Okay, then I don't have to do anything. We can take a break for this class. Anyway, so the idea was that I sort of will try to set up basically write down just the notations for most of the points that we'll cover in probability theory. And the plan is that this sort of sets up an introductory situation for John Renitz to take over. So John Renitz will cover classes from tomorrow. So he'll be talking primarily about maximum likelihood, p-values, Bayesian inference, and so on and so forth. So that's basically the idea. So in the second lecture, there I'll go into more like stochastic process. I'll try to derive the master equation and try to see how the master equation you can think of interpreting for the evolution of probability density, probabilities. All right, so since most of you are familiar, I'm just going to keep writing, and if there is something unfamiliar, just stop me and then we can discuss that. So you want to think about basically the ideas of probability. Probability and random variables, right? So simple idea is that you have some experiment, some observation that you see, and that has a certain set of outcomes. So you collect all the possible outcomes and define it, that set, as the sample space. So this is the set of all possible outcomes. And out of this set, you can pick out some event E, which is a subset of the sample space. And this is the set that you are interested in, so some set of interested outcomes. So for a given set of events E and F, you can define the following things, which are basic high school constructs that you think of. So one is to define the complement of E, which is all of S that is not E. So essentially E union E complement will be the whole space again. So similarly, you can define things like the intersection of two events, the union of two events, and so on and so forth. So if two events E and F are such that their intersection is a null set, what do you call E and F? Pardon me? These are mutually exclusive events. So general question, are we giving you enough coffee? You should speak up. If not, you can tell me, I can double the dose. Right, so that's basically defining a set of outcomes and then defining certain events and how to combine certain events. So, but we want to get to probability, right? So what's probability? So probability is basically what you would call a measure. Okay, measure of what? Be a measure of some uncertainty that is there. So we don't know the full information about the events. There's some belief that this is with a very likely event, and so on. Or in a more practical sense, it's the relative frequency with which some event occurs, say E occurs, in the long run. That means you repeat the process a large number of times and compute the relative frequency of the occurrence of a certain event E, and that gives you a measure of the probability of the occurrence of that event E. So some properties of the probability distribution. So I'll denote the probability distribution probability by P. So what's the probability of the entire sample space? 1. Something must occur. And you also know that for any event E, the probability is a non-negative number. And the probability of the union of two events is the probability of E plus the probability of F if E and F, or with the other way around, if E intersection F is the null set. That is, E and F are mutually exclusive. Now, since E plus E's complement is the whole sample space, what is the probability of the occurrence of E plus the probability of the occurrence of its complement? 1, right? So something happens or the complement of that happens. So therefore, their sum is 1. What about this one? If you have two events E and F, and you look at the probability of the occurrence of the intersection of E and F, how do you write this? Sorry, the union of E and F. Yeah, sorry, the union of E and F. So for general events E and F, which need not be mutually exclusive, so that turns out to be the probability of E and the probability of F, and the probability of the intersection of E and F. Most people are familiar with this, right? This is not something new. And so you can generalize to many events. So if you have a bunch of events, A1, A2, ... and they're all mutually exclusive, then the probability of the occurrence of A1 union A2 union ... is just the sum of the probabilities of each of the events. A2. And the practical way of computing these probabilities is usually by doing permutations and combinations. So people are familiar with how to compute permutations and n-choose R. So I'll skip that part. So let's go into some other aspects. The next notion that one would like to understand is the idea of the conditional probability. So sometimes called relative probability. So if you have an event F, and you want to find out that what is the probability of the event E occurring, given that the event F has occurred. So this is what is called the probability, conditional probability of E given F. So this you can immediately see should be just the probability of the intersection of E and F, that is both E and F occurring simultaneously, scaled by the probability of F occurring alone. I mean, in some sense, all probabilities are conditional, right? So because the probability of any event occurring E, I can also write it as probability of the occurrence of E given the entire sample space. So the probability of the occurrence of both E and F is the probability of the occurrence of E given F and the probability of the occurrence of F. So surely I can also do it this way. The probability of F given E times the probability of E. So what you infer? So you infer this very nice and simple looking formula, which has fantastic consequences in Bayesian analysis. The probability of F given E times the probability of E. What is this called? People are familiar with this? Bayes theorem. Theorem or formula. I'm going to skip examples of probabilities and things like that. I'm sure many of you are familiar with this. So that's defining probabilities on a given set of events and their sample space and so on. Next thing we want to look at is what is called random variables. That is, you assign numerical values to each point in the sample space. So a random variable is a function. So that takes on a numerical value for each point of the sample space S. I mean, the canonical example that we usually have is coin tossing. So you toss a coin and find out the number of times heads and tails occur. So let's say you toss 2 coins. So let's say 2 coins. What's the sample space? No. I mean, I've tossed 2 coins, so there are 4 possibilities, right? That both of them are head, both of them are tail. One is head, the other is tail, and the other is tail. And so I want to say the random variable. I want to say the following thing. So X is a random variable which measures the number of heads. So what are the values that X can take? 0, 1, or 2. Right? So you have a sample space, and to each point of the sample space, you assign a number. And that function is what is called a random variable. And so this variable can take, in this particular case, 3 discrete values, 0, 1, and 2. So one would like to ask now, what is the probability distribution of this random variable? Of X. So just let me put a disclaimer. Yeah, go ahead. Yes. No, that's the definition of your random variable. You can be anything from minus infinity to plus infinity, whatever you want. I mean, you choose that. That's what I mean. So this is the sample space we got. I can define. So this is also a function, right? That's the choice of the function that you make. Just count the number of heads, count the number of tails, count the number of events which has 2 heads. No, right? Because these two have the same value, which is 1 and 1. Yeah, so I'm looking at the probability distribution of X. So I just want to make a disclaimer. I'm trying to follow John Renitz's notes so that there's a continuity of notation. I probably will mess up the notation, and so sometimes use something for something else. So do bear with me. So I'll call this the probability distribution of X. And what is this probability distribution? So this is a list of the possible values of the random variable X and their probabilities. So for this case, just work out the following. So X can take values 0, 1, and 2. What are the probabilities of X? What's the probability of 1 by 4? One by 2, and then 1 by 4. So what we looked at right now is the idea of discrete random variables. So that means you have a countable set of values that the random variable can take, countable set of values. But you could also have continuous random variables. Can you give me an example of a continuous random? So you take values, for example, from an interval. Give me an example of a continuous random variable. Things that you talked last, height of evaporation, for example, the peak size of birds. So on and so forth, many, many examples. Now, given a probability distribution, that is the probability of the occurrence of X, you can also compute something called the cumulative probability distribution. Remember, P of X gives you the probability of the occurrence of X. But many a times you're interested, and this is also a very, very useful quantity, to find out the probability that X is actually below some value. The probability that X is less than or equal to capital X. So this, by definition, is just the sum of all the possible values of A, which are less than or equal to capital X, times the probability of the occurrence of A. So for the same case, can you compute for me the cumulative distribution? So first let me plot this out. Just chalk. So if you plot P of X, how does this look like? So there are values 0, 1, and 2. So 0 it is 1/4, 1 it is 1/2, and 2 it is 1/2. Tell me the probability, cumulative probability distribution. What are the values of that? For, sorry, 1/4, and then? So half plus 1/4, which is 3/4, and finally 1. Right? So if you plot that, I don't have that distribution. Okay. So that will look something like it's 1/4, and then suddenly jumps to 3/4, and then finally jumps to 1. Yeah. Sorry, it goes up and goes, so this will be 1. Okay. So I just want to summarize a bunch of frequently encountered random variable distributions so that one is familiar with these terms. So let's start with discrete random variables, and then we can go on to continuous ones. So one of the simplest is Bernoulli random variables. What's a Bernoulli random variable? It's a simple thing that most of you are familiar with. It's just something which takes on two discrete values, 0 and 1. And again, the canonical example is that of coin tossing. So you assign a probability for one value, say a little p, and the other one, by definition, should just be 1 minus little p. The second most thing which we encounter right from our school days is something called the binomial random variables. So what you do is to do n independent trials of Bernoulli random variables, and then find out what is the probability of obtaining, say, theta successes, n successes, for instance. Right? So you say the probability of obtaining a success. I mean, you define either 1 or 0 as your success variable. So you describe n Bernoulli trials and ask what is the probability of x successes. Simple example again. Say you flip 3 coins simultaneously. So you list all possible HHT and then HTT and then HTH, THH, THT, TTH, and TTT. Now ask the following, that I want to look at the probability. So first of all, I define my success as finding the number of heads. Now I ask you, what is the probability that I'll get precisely 2 heads? How do I compute this? So remember, theta is the probability of getting a head. So what are the events in this sample space which will give you x equal to 2? That's basically the question. Well, I said the probability of getting a head is theta, so it just can't be 3. You're assuming theta is half. I didn't say head and tail are equally likely. So there are basically 3 events which will give you 2 heads, right? So there is HHT, there is HTH, and there is THH. Yes, that's why I said that. So what's the probability of obtaining 2 heads? Theta into theta. And what's the probability of obtaining a tail? 1 minus theta. Is that clear? And that's the same for all 3 events. So therefore, you get 3 theta square into 1 minus theta. Generalize this and ask for the following. So I have n independent trials. And if I get some event A, and if I get A's complement, I call it a failure. And in each event, the probability of the success is, say, theta. And you want to find out the probability that there are X successes. How do you do this? So look at a particular sequence. So there are XAs and n minus x A complements. So what's the probability of this event? So it's theta to the power of x and then 1 minus theta to the power of n minus x. But how many such events are compatible with the condition that there are x successes? Basically, you have to choose something. So NCR, right? So probability of getting x successes is n choose r, n choose x, times theta of x times 1 minus theta. So that's your binomial distribution. Have people heard of the negative binomial distribution? So how do you define this? So you define this as you do n Bernoulli trials, independent Bernoulli trials, and define the probability of a success as theta, and ask what is the probability that there are R successes and X failures. And how many such outcomes are there? So remember, you want to look at the following sequence, right? So let's say you have a success, da 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 da, and so on, with many A's and A's complements and so on. So you look at the case where there are R minus 1 success events and X failures, and the last one is the rth success. You basically have to find out how many ways can you get this sequence just before the rth success. How many such sequences are there? I mean, that's easy to write. Right? So there are R minus 1 successes and there are K failures. So there are a total of R minus 1 plus K events to choose from. And then you want to find out how many ways can I choose R minus 1. So that's just this. Sorry, X. And so therefore, now if you multiply this by the number of, the probability of obtaining R successes and X failures, that gives you the probability of getting a binomial distribution with X failures and R successes for a given occurrence of a variable theta. No. So I want the following. So I want to find out the probability that I will get R successes and X failures. Yes, R plus X is n. No, but R plus X could be much larger. May not be, no? No. It doesn't appear anywhere. Do n trials. There's no guarantee that you will actually get R success. I mean, you may have to do more, you may have to do less. So it's not a conditional thing that there are R of them and then n minus R failures. It's not that. Just keep doing trials until I get R successes and X failures. So I mean, I can forget many Bernoulli trials. Just keep doing Bernoulli trials until you get R and X failure. No. Then, yeah, rest of them must have been failures. These are, yeah, A and A complement are mutually exclusive. So therefore, if you've got R successes, there must be n minus R. Yeah, in that sense, R and X are related by n. This is the Poisson distribution. So formally, you can just take the binomial distribution and look at the following limit, that you look at the binomial distribution and you look at the limit where the number of trials goes to infinity. The probability of the, what did I use there? Theta or X? No, I used theta. Theta goes to 0, but you keep p times, so n times theta to be some fixed number, lambda. one can just find out. So if you want to find out the probability of k successes, that is just n factorial by k factorial times n minus k factorial. And then it's a theta power k and a 1 minus theta power n minus k. Have people done this? I can skip this and just write the result. You know how to go from here to the Poisson distribution? Yes, no, maybe I've not had coffee. I don't know the answer. I'm asleep. Say something. No, okay. So let me just do that then. Okay, so lambda is fixed. And so therefore you also know that, therefore, by definition, theta will just be lambda by n. So put that back in there and get the expression for P of k. So that'll be lambda power k by n factorial times n factorial by n minus k factorial, k factorial times 1 minus lambda by k. This is lambda by n whole to the power lambda by n whole to the power of k. This is just putting the value of theta equal to lambda by n. So you can just play around with some algebra and get the following. So you'll get a lambda power k and a k factorial, which is what comes out nicely. And then you have the remaining thing. So it's n factorial by n minus k factorial and n power k. And then the 1 minus lambda by n to the power of n and 1 minus lambda by n to the power of minus k. So you should be able to recognize something as n tends to infinity. So as n tends to infinity, lambda by n, which is our theta, tends to 0. And in that limit, what is this quantity? 1 minus lambda by n to the power of n. What does this tend to? Yeah. E to the minus lambda. And what about the other one? 1 minus lambda by k to the power of 1 minus lambda by n to the power of minus k. As n tends to infinity, n is going to infinity, so this is going to 0. It's just 1. So what happens to the final probability distribution? P of k will therefore go to lambda power k e to the minus lambda by k. So this is the Poisson distribution. It's one of the definitions of E, no? As n tends to infinity. You see in this 1 plus 1 by n to the power of n as n tends to infinity is E. And so if you have something here, that's e power a. Okay, minus a. That doesn't do anything different. That's what I said here, no? Okay, sorry, yeah, that factor I didn't, right, sorry. Yeah, that factor is also there. So that will also go to 1. So in fact, you can just look at that. So that's n factorial by n minus k factorial times n power k. And this in the limit n tends to infinity will go to 1. N is much, much larger than F. Forget this, these two cancel. N is, yeah. I don't know why is it called a negative binomial distribution? I don't know why it's called that. It's called negative binomial. Okay, so that's some discrete random variables. So let me go on to continuous random variables and get some more standard examples from there. So for continuous random variables, rather than talking about the probability, you talk about something called the probability density. So you talk about the probability density. So which is really the probability of finding x between x contained in a small interval between x and x plus dx. So again, this probability density, which I will denote by the symbol f of x, is a positive definite number. And so the probability of x being between two values c and d is defined to be the integral of the probability density between c and d. So f of x dx, therefore, the probability of finding x between x and x plus. So in fact, it doesn't matter. You can do this, you can do that, you can do this, you can do that. The probability of being at that point is zero. It's a zero measure. Okay. The statement that the probability of the entire sample space equal to 1 will translate to the normalization of the probability density. Something you should be familiar with if you've done some quantum mechanics. Just like in the discrete case, you can define the continuous cumulative probability density. So which is the probability that you will find, so I'll use capital X less than or equal to small x. This by definition is just the probability of finding all x between right? So if you have some continuous distribution, the cumulative density is just the up to the point capital X is just this area from minus infinity up to the point x. Small x less than, small x is less than, yeah. And so by this definition, you can immediately see that the cumulative probability density and the probability density itself are related like so. So if you know capital F, you know little f, and vice versa. So I'll give you some examples of continuous distributions in some time, but let's look at another point. Suppose you want to look at functions of random variables. So you know that x is a random variable. And I have a function of x, which I call y. And since I know the probability distribution of x, I want to find out what is the probability distribution for y. So basically it's like a coordinate transformation, right? So if you know some x and you want to find out how a function of x behaves, given by h of x, and you want to find out the probability, how the probability transforms when you do this coordinate transformation from x to h of x. So do this for the first for the discrete case, then do it for the continuous case. In the discrete case, what you have is a set of discrete values. That's your sample space. And you basically have some probabilities associated with those points. So that's your X space, right? So this is your X space. And so if you do a transformation from X to Y space, and the two are related by h of x, so you're basically going to deform this. Maybe this comes close by, this comes far off, this comes close by, something like that. That's your Y space. However, the probabilities themselves cannot change, right? So because they're just discrete numbers sitting there. So they'll exactly be the same. This one will be longer, this one will also be longer. Yeah, y has to be a monotonic function of x. Y, it's easiest if it's a monotonic function of x. So the only effect of the transformation in the discrete case is to just rearrange the spikes. So there was spike at the discrete values that x could take, but there is a mapping from the discrete values that x could take to the discrete values that y can take. And so the spikes just move there. So the height of the spikes are unchanged. In the continuous case, yeah, it should be no flipping things. No flipping. Yeah. No, why? Why should it be that way? It should be a one-way distribution, right? So why should be no a monotonic distribution? Some functions, right? That's a monotonic function. It can locally go up and down. Not the function, the derivative can go up and down. Yeah, so that's the point. I mean, going up and down is here the derivative, not the function itself. Okay. In the continuous case, however, so remember the probability density must be 1 over all space. And that should be the same as the probability density. I don't know what I call it for y. Okay, I put a subscript here. That should be preserved, right? And both should be equal to 1. So in this case, the shape of the distribution also changes. Such that the area is preserved. And how does that distribution change? What is the key word that one uses to do this transformation? What is it called? It starts with a J. Jacobian, basically. So Fy will just be Fx with let me just redefine this. This is h of x, and so y is equal to h of x, and x is equal to g of y. So this will be just fx of g of y times the Jacobian, so which is dg y. So this is the rescaling factor between the x distribution and the y distribution. All right. I'm going to skip that part. Let me give some examples of continuous distributions, and then I can go on to some moment generating domain. Several examples, first among them being the exponential distribution. So that is, given a theta, the probability of success theta, you define your and a variable for x greater than 0 and 0 for x less than or equal. But that's the point, it should be monotonic, no?
So if you have many peaks, so
it's not a monotonic function.
Right, then how
there are ways to do that, and I don't know if I want to get into that here. You can do that. The other super famous example that every physicist should know is the standard normal distribution. Probably the only one that we are taught, and forget everything else. So that is just the definition. E to the minus x squared. So this itself is an example of a case where it's non-monotonic, right? There are two parts to the thing. One is monotone increasing, the other is monotone decreasing. So you can take the two parts separately and work out this transformation. All right, so that was about distributions. This is essentially what it was. Can I go on? Go on to the next step, trying to describe distributions by what are called moments. So how do you describe a probability distribution? So one is you give me the probability distribution or the probability density function describing a probability. So if you give me the full f of x or p of x, then I'm done. I'm basically done with the full story. But many a times it's not possible to get that. So what you do is to resort to coarse-grained descriptions. So a few numbers which can characterize where is the distribution located, how much has it spread, and so on and so forth. These are essentially what are called the moments of the distribution. So first moment you define is what is called the expectation. That's sort of the center of gravity of the distribution. So the expectation value of a probability distribution, E of x, that's the notation that's used. In the discrete case, you sum over all the sample space points x and compute this sum, x times p of x. And in the continuous case, just be the integral used f of x. So surely the expectation is one measure to tell you where the weight of the distribution is concentrated. But then that's not the only measure, right? So I mean, you could have many distributions which have the same expectation value but have different looking shapes. It's more important to characterize that. So we'll come to that. So to go to that, a simple question to ask is the following. Suppose I have this random variable x, and I have a function of x. What is the expectation value of the function of x? Just yeah? Yes? No? Why not? It's a function of the function. So suppose it's a linear function, then it'll just scale and shift a bit here and there, that's all. But if it's a nonlinear function, not in general, right? Very likely no. So you like to find out the probability, the expectation value of a function of a random variable many a times. And so the easiest way to find that is just use the definition. I'll just write it for the continuous case, but surely you can generalize it for the discrete case. So this will be h of x, f of x, dx. Just as an exercise, compute the following. So if I give you the exponential distribution, theta e to the minus theta of x, or x greater than 0, what is the expectation value of x? What's the answer? Can you do that integral quickly? Simple integral using the definition, you'll find it's 1 by theta. However, if you compute the expectation value of x squared, that turns out to be 2 by theta squared, which is not the same as the expectation value of x, the whole square. The expectation is the first, what is called the first moment of the distribution. So one can easily define higher moments of the distribution. So before you go to that, you can actually look at certain linear transformations. So for example, if you have the same function h of x, but this time it's a linear function of x, then what is the expectation value of h of x? What will this be? It will just be a times the expectation value of x plus b. Just shifts and scales. The next thing you define, which characterizes the width of the distribution, is what is called a variance. So where now the function h of x is a measure of how far away from the mean value is the value of x. This is square. So the variance of f of x is just the expectation value of this quantity. X minus the expectation value of x, the whole squares expectation. And typically you denote it by sigma. Sigma is sometimes called the standard deviation. How do you calculate the variance? I'm sure you would have all seen this. So this, if you work out the simple algebra from the definition, will turn out to be the expectation value of x squared minus the expectation value of x, the whole square. So check that for the exponential distribution that I wrote down. Okay. I'm not going to go into examples of how to think about variance and all. I'm sure you all know that. So let me go to something called the moment generating function, which is a useful thing to learn. Then I'll come back to multivariate distributions. So continuing this way, you can define the rth moment of the distribution the following way. So you define the expectation value of E minus the expectation value of x whole to the power of r. The first center, this is a central moment, r central moment. The first central moment is 0. The second central moment is, by definition, the variance. And so one can keep defining these things. But there's a nicer trick. So what you could do is to define this function called the moment generating function. And find out its expectation value. So the moment generating function, m of t, is just the expectation value of e to the t times x. Why is it called the moment generating function? Well, I mean, it's easier. If you just look at how m behaves around t equal to 0, that gives you all the possible moments of the distribution. And that's why it's called, it sort of generates the moments of the distribution. So by definition, this is just e to the tx f of x dx. What is the derivative of m with respect to t? Work it out from that integral. So that will just be x times e to the tx times f of x. And so therefore, let's use the notation m prime. So m prime at t equal to 0 is the expectation value of x. You can work out the second derivative and evaluate that at t equal to 0, and you can show that that's just the expectation value of x squared. A simple process, just the differentiation again, and then take t tending to 0. So one can generalize this, and so the rth derivative of the moment generating function evaluated at t equal to 0 gives you the expectation value of x bar. There's a nice correspondence. So that is, if you know the probability density function, you know you can go back and forth between that and the cumulative density function. But there's also this, that if you know the moment generating function, you can go back and forth between the other two. If the moment generating function exists around the interval near 0. I mean, this is a way of characterizing this, right? So one is you tell me the complete probability distribution, or you tell me where the mean is, how far it is spread about, and how far the spread is spread about, and so on. So if you characterize everything, if you know all the moments, you can reconstruct the probability distribution. And so the moment generating function has the same information as the probability density function as well. Some simple examples like we saw earlier. So let's look at a linear transformation. So I know that the moment generating function of x is mx of t. How do I find out the moment generating function for y? Plug in the definition and do this calculation. I'll leave it to you. And show that this is just a simple relation between the two moments. So So if you have two independent random variables, or one can generalize this to n random variables x and y, and you look at the sum of the two independent random variables, the moment generating function for the sum will be the product of the moment generating functions for the individual. You can measure the symmetry about the mean, for example, that gives you a skewness, there are kurtoses, and then I don't know the names of the higher moments. Third and fourth moments, yeah, there's lots of names for them. So that tells you, first thing tells you where it is located, the second tells you how much of a spread it is about the mean value, the third tells you how asymmetric it is about the mean value, and so on and so forth. So as an example, work out the moment generating function, the normal distribution. Erase that. So for the standard normal distribution, so what is the moment generating function? Work out this. The standard Gaussian integral that we all. Again, I'll leave it to you. It's a simple exercise in completing the squares. Once you do that, you'll find that the moment generating function is just e to the t squared. Okay, so that's a nice way of coming to something that we all learn at a mother's knee in statistical physics, the first class, something called the central limit theorem. So look at the following. So suppose I have n random variables which are identically distributed and are independent. So distribution need not be a normal distribution. It could be any distribution. The only thing is that they are independent and they are identically distributed. They all have the same distribution. So if you have n IIDs, so independent, identically distributed random variables, and they have some cumulative density function f. I want to look at the following quantity, so which is the sum of the n identically distributed random variables. And I particularly want to look at the following, that if I look at a large number of such random variables, the limit n tends to infinity, I would like to ask what is the probability distribution for Sn. Suppose each of the distributions, IIDs, are such that their expectation is 0. I mean, you can scale it, you can shift it around if it's not a big problem. And their variance is some positive number, sigma squared. For the simple cases, yes, but one can generalize this to non-identically distributed case. The variance has to be finite. I think that's all. The sigma square should be bounded. It should be non-infinite. So if you define some scaled variable, Zn, which is Sn divided by sigma times square root of n, and look at the moment generating function for Zn. So mZn. Remember, all of them are independent random variable. They're identically distributed. So it will just be What did I call that? I didn't call it anything. So it will be the moment generating function of the n variables multiplied with each other. This is Sn, not Zn. So if you scale this now by sigma root n, so that will just be the moment generating function by sigma root n, whole thing raised to power n. So you can just expand the moment generating function around 0, and you can work out by doing a simple Taylor expansion pretty easily that the moment generating function for Zn, which is the same as t by sigma root n, will turn out to be 1 plus t squared by 2, 1 by n, simple calculation using the fact that the variance is sigma square and the expectation value of each of x is 0. It's not a rigorous derivation. This is just a hand-waving argument to show that this will turn out to be the Gaussian. So then the moment generating function for Zn will approximately be the same as 1 plus t squared by 2, 1 by n, whole to the power of n. And in the limit n tends to infinity, this will turn out to be e to the t squared. So which is the moment generating function, mgf, for a standard normal distribution. So if you look at the sum of n identically distributed random variables, that goes to a normal distribution in the limit that the number of variables is infinite. These people have seen most of them. Yeah. I'm also probably lost since this is not my notation, so let me go slow. So I call m the moment generating function for each of the variables. And so Sn is the moment generating function for this variable, which is just m of t raised to the power of n. I defined a scaled variable Zn with sigma root n, and that is that. And this is just t replaced by that, whole to the power of n. So I'm just going to calculate this distribution. So m of t by sigma root n. So you can do a Taylor expansion. Whole to the power of n is what you want. And that in the limit n tending to infinity will turn out to be the Gaussian. There's something else. Huh? So people have seen this, right? The central limit theorem, everybody has seen. Okay. Okay, so that's about what I had to say about these distributions. I'll do a little bit about multivariate or joint distributions, and then I can stop. Next time I'll talk about stochastic process and trying to write down the master equation for the evolution of probabilities. So far we have looked at one random variable or many trials of one random variable. So one could really look at multivariate random. So that is the 2 or more random variables and ask for joint probabilities. The probability that one takes one particular value and the other one takes another particular value. So multivariate distribution or a joint distribution is looking at the multivariate or is looking at the probability distribution of several variables, more than one. So you can look at the simplest case, which is the bivariate, just 2 random variables, x and y, let's say. So what's the statement here? The statement here is that if you want to look at the probability of little x and little y, that is the statement that the variable x takes the value x and the variable y conditional on both the variables x and y. So surely, just like the earlier case, if you have summation over all x and summation over all y, this should normalize to 1. So this joint probability distribution, you can compute what is called the univariate distribution or the marginal distribution. This is an important thing. So this is essentially what Amitabh Joshi was talking about. So you look at the probability distribution of a particular trait, but then you don't worry about what are the distributions of other traits. So you just average over all possible values for the other traits, and you just look at the marginal for a particular trait, marginal distribution for a particular trait. So for example, you can look at the marginal distribution for x alone, which would be the following. So you just don't worry about what value of y it takes, so you just average over all possible values of y, and that defines the marginal distribution for x. A similar thing for y. So one is to talk about the joint distributions. The next is to talk about the conditional probability. So we'd like to find out the following, that given that we have found the value little x for the variable capital X, what is the probability that you'll find the value little y for the variable y? Right? So this is the probability that y, capital Y takes the value y, given that capital X has taken the value x. Which from our earlier discussion on sample spaces and all, you can really see that this should just be the probability that x takes the value little x and y takes the value little y, scaled by the probability that x takes the value little x. So the conditional is just the joint divided by fx. So if x and y are mutually exclusive, that is x and y are independent random variables, then the conditional will just factorize, right? So this, what will this become? If y and x are independent, then p of y given x will just be y, when it doesn't care about what the value of x was. So I'm skipping a lot of examples and all. I'm sure you guys have seen these. They must be independent. So yeah. This factor is p of x, y is p of x into p of. Let me just write. These are independent variables, then p of x, y is just p of x into p of y. Okay. A similar thing one can write for continuous random variables. I want to end. How do you describe multivariate distributions? And that's a good point to stop. So if you have a multivariate distribution, so now I've gone to a continuous bivariate distribution. And so I have the probability density f of xy. So f of xy dx dy gives you the probability of finding x between x and x plus dx and y and y between y and y plus dy. So for this continuous variable distribution, continuous bivariate, you can also define the expectation values, just like we did earlier, right? So we could look at the expectation value of a function of both x and y, which is just dx dy h of xy f of xy. Suppose you look at h to be just the sum, then the expectation value, the sum of the two variables, will just turn out to be the expectation value of x plus the expectation value of y. And one can, as I discussed earlier, work out the marginal distributions as well. That is, averaged over x, one can find the marginal distribution for y, or averaged over y, one can find the marginal distribution for x. However, in the case of multivariate distributions, just the marginals will not tell you the full information. One is to get the expectation values of x and y separately. So there's probably, you need to give the full distribution. So also it's, you can't draw multivariate distribution. It's really a surface in 2 dimensions. So a better way, and one number which is very useful, is what is called the covariance of x and y. And the covariance of x and y is defined as the expectation value of x into y minus the expectation value of x into the expectation value of y. So x into y is just thinking that h is a function which is xy and finding out the expectation value of xy. One can look at some, I'm going to skip that. Last quantity, which really measures and is related to the covariance, is the correlation. So the correlation of x and y, that is to find out how correlated x is with y, is just defined as the covariance of a scaled variable. So you just measure x away from its mean value and scale it by its variance, and similar for y, sigma y. Because sigma x and sigma y are just scale factors, this just comes out and you can show that this will just be. So this number is sometimes called correlation coefficient. Yeah, once you do it for 2 variables, you can easily generalize it to n variables, and so it's not a difficult thing. Okay, so just as a summary, what we did was to define random variables. So first define probability, then define random variables, and look at probability distributions, cumulative distributions, how to characterize distributions by looking at their moments, the moment generating function, examples of discrete probability distributions, continuous probability distributions. And then we came to the last topic of looking at multivariate distributions, and the bivariate case in particular. And we looked at one is the marginal distributions, and then trying to compute how x and y are correlated by measuring either the covariance or the correlation coefficients. Okay, good. So I'll stop there, and I'm at a good point, so John can take over from here. So next class, I'll do some stochastic process, and we'll try to derive the master equation for that. Good. Okay, I'll stop there.
Hello. I have this question in my mind for some time. So when you look at these continuous random variables, the probability that a continuous random variable takes a particular value is kind of zero.
Zero.
So what does that mean? I mean, is it saying like that the proportion of, let's say if you are talking about heights, that the proportion of people having a certain height is very small. Is that what it's saying, or is it like...
No, the probability of having I mean, it's like a real number thing, right? So what's the probability of getting one particular real number is what you're asking. That doesn't have any width, so it's zero. It's zero measure. I don't know how else to answer that. Anything else you can have? Is zero, yeah. It's like a... Yeah, exactly. Yeah.
So, hello. Yeah. So, binning of the histograms, I think, matter here.
In a process of random walk like Brownian motion,
Yes.
Where a particle is expected to flip around a steady state, how
It may or may not be a steady state, but fine.
not a steady state, but around
Okay, go ahead.
a mean point. Yes. How can we use all tools to really determine the vibrational state that result?
I don't know what you mean by vibrational state, but one can characterize quantities like what's the mean position, how much the particle is spread around, and I don't know what is meant by a vibrational state. If you have something like you tied it to a spring, and
what I want to say is, because when a particle move around its around a mean position,
yes,
they are energetic. There are energy to be taken into account, and what I want to know is how probabilities or density. How can we use density probabilities to determine if we have a lot of particles, if we want to study a system of.
So I mean,
because as I'm saying, these we are studying these tools you have given us. It is good, or it is better to understand and interpret as well as possible a system of only one or two particles. But how can we use it to
many particles?
For a
I
system?
mean, like I said, I did the bivariate. One can generalize this to n particle distributions.
At this moment, is it better to use a continuous or a discrete?
Depends on what you're looking at. For example, if the particle is moving around in continuous space, it's a continuous variable, say particle in 2 dimensions.
I'm asking if we have a system of too many particles.
Yes.
It is good to use discrete probabilities or continuous probabilities.
Again, it depends on what you're looking at. If you're looking at individual particles, then there are n particles. It's a function of n particle positions. I don't know. You could coarse-grain it and look at it like a density field, and one can write down probability distributions for the density field as well. That's also a possibility. I'll try to do the random walk when I do the master equation. Maybe then you can get back.